consequences of directing attention. Now let's look at the effects of attention on visual behavior and neural responses. Since attentional selection is before the visual decoding or seeing stage, by definition, attentional selection makes visual decoding better. That means makes visual performance better. And this better performance means faster and more accurate performance. So when you measure the performance in validly cued trials and compare them to the performance in invalid cued trials, and this can be queuing by top-down queuing or bottom-up queuing, and so in validly cued trials, the reaction times can be shorter or the performance accuracy can be higher. And these effects can be quantified as the queuing effects. For example, in this study, observers need to report whether the letter T is right way up or upside down, and they are exogenously or endogenously cued to expect that the letter will appear in the upper right corner rather than at these three other locations. And if in 80% of the validly cued trials they do this correctly, but only in 70% of the invalid cued trials they do this correctly when the letter appears at an unexpected location, then this difference of 10% is the queuing effect. And queuing effect can also manifest in reaction times. For example, if the reaction time in the validly queued trials is only half a second, but it becomes 0.7 second in the invalidly queued trials, then this difference of 0.2% is a measure of the queuing effect. The magnitude of the queuing effect, of course, depends on whether the queue was exogenous or endogenous, and also depends on the details of the visual task. The queuing effect depends on the difference between the onset time of the queue and the onset time of the test items, and this difference is called SOA, for stimulus onset asynchrony. Exogenous queuing is fast, most effective for short SOAs smaller than 200 milliseconds, and it's transient and diminishes by SOA longer than 400 or 500 milliseconds. And endogenous queuing is slow and most effective for longer SOAs larger than 200 milliseconds, and it's sustained and long-lasting. When they are in conflict, exogenous queuing can override endogenous queuing where SOA is short. For example, if after this endogenous queuing before the test items appear, we insert an exogenous flash at another location, and even though this queue is to the upper right location, you flash at some other location, then attention will be dragged to the flashed location, and this queuing effect by endogenous queue will be ineffective. And also, exogenous queue is difficult to ignore. So for example, if you tell human observers that the location of the flash has nothing to do with where the location of the T might appear, so that this is actually uninformative, the queuing effect will still be there. However, if it's in the endogenous queue, then observers will completely ignore this because it's uninformative. Now let's look at the effects of attention on neural activities. These effects are mostly studied under top-down attention, and they are observed in neural activities in extrastriate cortices like V2, V4, IT, and MT. And these effects in V1 are relatively weaker or non-existent. The experimental design is often like this. Here is the display screen. The monkey fixates on the central cross. This dashed box marks the residual field of a neuron being recorded. But of course, this dashed box is only for illustration here, and it's not shown to the monkeys in a visual display. And in this residual field, it contains two visual items, in this example, two bars. And often one of these items, for example, the orientation of the bar, is preferred by this neuron, and another one has a non-preferred feature. And the experiment can also have visual inputs outside the residual field. Monkeys are trained to covertly pay attention to one visual item. Let's say this one. Yeah. For example, the monkey may be trained to detect any color change in this bar. So presumably its attention is on this bar. Meanwhile, the neural activities are measured while the monkey does the task. So, for example, we can see how neural activities depend on whether the monkey is paying attention to this bar, or this bar, or this bar. This way, it has been found that if there are two items inside the resident field, and if the attention is directed somewhere outside the resident field, then the neural response to these two items together is the average of the responses to each of the two items presented alone. However, directing attention to one of the two items inside the resident field makes the neuron respond as if the other item is absent. These neural response changes are not caused by any change in the retinal input, because in all situations, the monkey has to keep its gaze fixated on the central cross. So the neural response change is caused by a change in where the monkey pays attention to. Another experimental design is to have only one item within the receptive field and examine the attentional effects. In more detail, let's say this is the response property of one neuron. Its response increases with the input strength within the receptive fields. If attention is directed towards this receptive field, you can see typically an increase in the response. So the blue curve becomes the red curve. That means attention increases the sensitivity of this neuron. Attention can also change input response curve in other ways. In this case, this is as if attention increases the effective input strength. You can also measure the feature tuning curve of a neuron. So, for example, let's say that this is the orientation tuning curve of a neuron. So the feature value is the angle theta of the bar within the receptive field. And here is the preferred orientation. Attention to the receptive field can change this tuning curve, for example, to scale it up or to change its shape so that the feature tuning width is smaller or larger depending on whether the attention is to this receptive field or not. Yeah, and these kind of phenomena is called biased competition, meaning that visual inputs compete for being represented in the brain, and top-down attention to an input item or input feature biases the competition so that more brain resources are used to represent the attended input. So far, only one study showed how neural responses are affected by bottom-up attentional attractions. It studied attentional effects on V1 neurons. This is the fixation stimulus in the study. The monkey fixates on a central point, and this is the receptive field of the neuron being measured, and then the exogenous cue flashed after a pause, and the probes appeared. So we can then measure the neuron's response to the probe inside the receptive field. Here the probes are just the gratings inside outside the receptive field. And we can examine how the neural response to the probe inside the receptive field depend on whether the cue is around the receptive field or away from the receptive field. This is neural response versus time. At time 0 is when the probe appeared. The darker curve is for when the cue is on and around the receptive field, and the lighter curve is when the cue is away from the receptive field. And so this cue on is a validly cued trial, and cue away is an invalidly cued trial as far as this neuron is concerned in response to this probe. Yeah, and before the neural responses to the probe happened, the neuron actually responded to the cue when the cue is on, but not when the cue is away. And you can see the cue appeared roughly a bit more than 100 milliseconds before the probe appeared. However, by the time the probe appeared, the response to the cue has already died down, and the initial response to the probe is independent of where the cue is. However, at around 100 milliseconds after the probe appeared, you can see the response to the probe is much higher when the Q is on the receptive field. That means the neuron's sensitivity to the probe is increased due to this Q. Now, however, because the neuron also responded to the Q, even though by the time the probe appeared, the Q disappeared and the response to the Q has already died down, one can never be sure whether this increased response is not actually due to this Q. Yeah, the Q may be a confound, we can't be sure. Yeah, and so one way to resolve this is to simultaneously flash two Qs, one on the receptive field and one away from the receptive field. In this double Q case, the neuron responds to the Q inside its receptive field as it should, but there's no enhancement to the probe. So therefore, just having a Q to the receptive field is insufficient to cause a probe enhancement. It also requires no competition from the second Q for attentional attraction to the receptive field.